All right, so we are looking at the sampling distribution of the mean, or x bar. This is just like what we did for proportions in 7.2, only this time it is with means. So it's the same general idea, just with a mean instead of a proportion, so our formulas have to change a little bit. So this is the distribution of x bar in all possible samples of size n. So again, that's every possible sample for a certain size. So you would have a sampling distribution like for n equals 5, and that would differ from your sampling distribution for n equals 10, for example. So just like with proportions, we're going to look at the mean of our sampling distribution and the standard deviation of our sampling distribution. So here we say mu of x bar. So again, this is if I took all possible samples of a certain size, put all of those x bars together, the mean of those is just going to be equal to the population parameter, or just mu. The standard deviation then, so just like for proportions, there's some stipulations. This we can only use if 10 times our sample size is less than or equal to our population. So again, little n is sample size, big N is population size. And our formula for this is that sigma sub x, so standard deviation of all of those x bars together, is equal to the square root, or the standard deviation of the population over the square root of n. Okay, so these are actually both on your formula sheet as well, but you do need to know this, of when that can be used. Okay, thinking about shape then. So this part differs from proportions the most. So the sampling distribution of x bar is normal if the population distribution is normal. So we're actually going to look at another option in our second set of notes for 6.3, but for now we're going to say the sampling distribution is only normal if we're given that our original population is normal. So this piece would have to be given. If it's not, then for now we don't know what to do with it. So we'll look at that later on. So let's look at an example, page 462, number 56. So we are looking at cereal. We have a company cereal boxes advertise 9.65 ounces of cereal. In fact, the amount of cereal in a randomly selected box follows a normal distribution with a mean of 9.7 ounces and a standard deviation of 0.03 ounces. So I'm just going to record what we're given. So they tell us this is normally distributed with a mean of 9.7 and a standard deviation of 0.03. So this is if I were to just select a single box. Okay, so in part A, they say, what is the probability that a randomly selected box of cereal contains less than 9.65 ounces of cereal? So what I'm looking at here is they are talking about a single box. They are not talking about a sampling distribution because our sample would just be 1. So for this is just plain old the probability that x is less than 9.65. Okay, so I'm not looking at a sampling distribution, so I don't need to use these formulas here. But I can use the given information because this is for a single box of cereal to create a z-score. So z would be less than, when I make a z-score here, I would do 9.65 minus 9.7 divided by 0.03, so I get a z of negative 1.67. So what I'm thinking about on my normal curve, so I have a negative z-score, so somewhere over here, and I'm looking at less than, so I'm interested in this area. So to find that, I would do normal CDF in my calculator. So we get 0.0478. Okay, let's look at part B then. So they say now we're taking an SRS of 5 boxes. So I'm going to record that n equals 5 because 5 is my sample size. What is the probability that the mean amount of cereal x bar in these boxes is 9.65 ounces or less. So this is not looking at the individual box. They're going to weigh all 5 boxes, and then they're going to calculate the average of those 5. So what we want to think about is how would that vary if we were to do that for many, many boxes? And that's where this information comes in. So I want to look at the mean of X bar first. So I know the mean of X bar is just equal to mu, which here is that original mu, so 9.7. Before I look at standard deviation, remember this has to be true. This 10n is less than or equal to big N. So I'm going to say 10 times my little n, which is 5. So 50. All right, so this has to be compared to the population, which would be all cereal boxes of this size. So it's definitely safe to say that there's more than 50 of these. So we're going to say this is less than the number of boxes of cereal produced. So a lot of times that'll be kind of a general statement like that where you don't know the exact population, but you can definitely use common sense to say that it's definitely got to be bigger than 50 in this case. So then that means we are okay to use that standard deviation formula that was on the first slide. So I would just have sigma of X bar is equal to that original standard deviation that we were given, so 0.03, divided by the square root of my sample size, so 5. So I get a standard deviation here of 0.0134. So what this means is when I'm looking at sets of 5 cereal boxes at a time, because originally it was normally distributed, it's still going to be normally distributed with a mean of 9.7, but now my standard deviation is 0.0134, which makes sense that the standard deviation is smaller because I have more information. I'm looking at 5 boxes and calculating an average. So if I happen to have a box that is, kind of unusual either in terms of less than or greater than, that's going to be balanced out by the other boxes, so there's going to be less variability. So we then want the probability that this set of 5, or the average of this set of 5, so they call that an X bar because it's from the sample, is less than 9.65. So we're going to want to find the z-score, and this time the only difference is when we're finding this z-score, we're still using 9.65 and 9.7, but my standard deviation has changed to 0.0134. So that gives us a z-score of negative 3.73. Okay, so anytime I use that normal CDF, I want to draw a curve of what we're looking at. Negative 3.73 is going to be way over here. So a very tiny area. So just this little piece here. So that, using normal CDF, gives us 0.001. Oops, I missed a 0 in there. 0.0001. Okay, so that's really it for sampling distribution of a mean. We have our formulas for mean of X bar and standard deviation of X bar. And as long as our original population is normally distributed, we can use those normal calculations. So let's have you guys go ahead and give this one a try. So remember, this is where you pause, try the check, come back and see how you did. So I'll first give you the answers, and if you've got them and you're good to go, you can move on. Otherwise, I'll go through and explain. So if you need to listen to that, I will do that as well. All right, so we are looking at human pregnancies normally distributed with a mean of 266 days, standard deviation of 16 days. So number 1, we have 0.4013. So this would mean there's a probability, or a 0.4013 probability of selecting a woman whose pregnancy lasts for more than 270 days. Number 2, when they asked us to calculate the mean, that would be 266 days. Number 3, the standard deviation of x bar is 6.532 days. And we can do that because 10 times 6, which is our sample size, so 60 is less than the number of all pregnant women. And then in number 4, when we were looking at the probability that x bar is greater than 270, that is equal to 0.2701. So if you were good on those, you are welcome to end the video. Otherwise, I will look at them. If you need help with any of them, you can fast forward to the part you need. All right, so for number 1, we're given that the population is normally distributed, and we're just looking at one woman. So we don't need to do any calculations initially. So this is the probability that x is greater than 270. Okay, so I can just go ahead and make a z-score out of this. So I would do 270 minus my mean of 266 divided by my standard deviation of 16, which gives us a z-score of 0.25. So then I would do normal CDF on my calculator. See, 0.25 is going to be somewhere here. And I'm looking for the greater than part, so I'm looking for this area over here. So normal CDF then gives us 0.4013. Okay, number 2 then was simply asking us to calculate the mean when I'm looking at that set of 6. So the mean of x bar is simply equal to the original mean, which is 266 days. Number 3 then was asking us to look at standard deviation. So what I would want to look at first, or say, would be that 10 times my sample size, which is 6, equals 60, of course, is less than my population, which is the number of pregnant women. Okay, so that means we're okay to go ahead and calculate that standard deviation. So the standard deviation of x bar is going to be equal to my original standard deviation, so 16, divided by the square root of my sample size, which is 6. So in other words, we get 6.532. All right, and number 4 then, we're using the information from 2 and 3 to calculate our z-scores. So we want, this time, the probability that not x, but x bar is greater than 270. So not for a single woman, but the average for a set of 6 women. So same idea. I'm going to use 270 minus my mean here, 266, divided by this new standard deviation that we just created to get the z-score. So the probability that z is greater than, we get 0.61 for that z-score. So then thinking about my normal curve, 0.61 is about here. And I'm looking for greater than, so the area to the right. So that would mean, using normal CDF, I get 0.2701.